Okay.
Well, I'd like to welcome everybody to this week's edition of the Water Talk. Today's speaker is Jeff Snider, an assistant professor here at the University of Wyoming in the Department of Atmospheric Science. Jeff's a recent graduate of the same department. He lists his interests as the chemistry of cloud water and precipitation and the study of biogeochemical cycles. Today he'll talk on the chemical composition of snow and cloud water at the Elk Mountain Observatory. So Jeff, welcome to Water Talk.
Thanks. I must admit I'm not used to standing up here in front of all these TV cameras. I don't know how to turn off the lights, so. Can you, Jeff, are you? How about this one too? Thanks. No. All of a sudden I lost my notes. Wonderful. Did you take something off the podium here?
What are you looking for?
My notes that I put on the podium. Yeah, there we go. All right. Nasty trick. Now we need some light here too. Well, I want to start off by just describing where Elk Mountain is. I'm sure most of you know that. And talk about some of the things that we've been doing up there. Over the last 4 years, I did my research for my PhD dissertation at the Elk Mountain Observatory, which is at the summit of Elk Mountain, shown here in this picture. The view here is from an aircraft looking towards the southwest. On the far horizon, on the western horizon, is the Sierra Madre Range. And the town of Saratoga is in the North Platte Valley on the other side of the summit of Elk Mountain. Now, the area surrounding Elk Mountain is dotted by a number of ranches. There's not much activity, so it's a fairly remote site as far as the chemical composition of the air and snow which falls on the summit of the mountain. One interesting thing that you can see in this picture, and also I'll point out later, are these regions here where there's some evaporite deposits. These materials tend to be alkaline, sodium bicarbonate or calcium carbonate type deposits. There are rather large areas of large playa lake areas upwind that also contain these deposits, and it appears to be an important source of alkalinity for the aerosol in this region, which is eventually incorporated also into the snow and possibly into the cloud water. Now, the forest at the top of this mountain is an alpine ecosystem composed mostly of spruce, and then there's a transition into Krumholtz type species and then tundra. The picture here was taken in the fall many years ago, but you can see just a dusting of an early season snowstorm. Now, this north ridge that was shown in the right-hand picture there is the ridge we drive up to get to the top of the mountain, and that's shown on the dotted line, which follows Halleck Creek from near Palms Ranch at the base of the mountain, and it comes up this north ridge to Elk Mountain Observatory right here. The summit of the mountain is this eastern summit right here. It's above 11,000 feet, and then there's a small ridge to the west where we have another building called the Schaefer Hut. Now, down near tree line at about 8,000 feet is a Brush Creek site, which is a temporary building that we installed for doing some experiments which involved releasing sulfur dioxide into clouds, wintertime clouds at the summit of the mountain to study conversion of SO2 to sulfuric acid. And I'll talk about that experiment towards the end of my talk. Well, inside the observatory, this is a picture now taken inside Elk Mountain Observatory. You can see a fairly versatile data system. It records something like 9 channels of meteorological data, both from the Schaefer Hut and from an observation platform right at the observatory. And then also recorded in addition to that is any auxiliary data in analog form. There's 4 channels for any auxiliary type analog data, one of which is being used here for the sulfur dioxide monitor. Data is recorded on tape, magnetic tape, and then analyzed here at the Department of Atmospheric Science. There's also facilities for 6 people, shower, kitchen facilities, all the accommodations you would expect, and pretty nice place for doing experiments at this elevation. Now this is a wintertime picture taken of the observatory. As you can see, it kind of sits in a depression with the summit. This is looking towards the east, the summit of the Elk Mountain behind this closer tree-covered ridge. Access is in these Tucker snowcats. And then there's this observation platform west of the observatory where I've mounted a cloud water sampler, which I'll show in a little bit for collecting cloud water. The wind tunnel right here is used to pull air in here and then down past some instrumentation which can be used to measure both cloud droplet sizes and their number concentration, and then there's some other instrumentation that we've used on occasion to measure snow crystal sizes and also their concentration and actual crystalline morphology. Now this is a picture taken in the wintertime showing what we call an isolated cap cloud. These clouds are not very deep. They're only a few hundred meters in depth. They extend for at most 10 kilometers. So essentially the air flows horizontally with a bit of an upward component on the windward side. Air flows up the mountain and condenses at the cloud base to form cloud droplets, which in the wintertime are super cooled. Their temperature is below freezing, so if they touch an ice surface, they'll freeze and form what we call a Rime Ice deposit. As far as precipitation from these clouds, that is snow, there really isn't any. There's not enough time for ice crystals to form and fall. Any ice that does form in this cloud essentially is carried by the wind and evaporates on the windward side, on the leeward side, excuse me. Now this simple cloud shape and flow characteristics allow one to do studies of, say, chemical kinetic processes in a very simple cloud where, as you can probably tell us by looking at this picture, there's a rather easy relationship between the velocity, say, of the air and distance, and there's an easy way to relate that to time for reaction within the cloud. Now back at the summit, this is looking towards the east. The sun is setting behind the photographer here. You can see examples of this Rime deposit on trees. The observatory sits down in this small depression over here, and this is the summit of Elk Mountain, where there's a small building that originally was a fire lookout used by the Bureau of Land Management. Now this stuff on the trees here is a combination of snow and what we call Rime Ice. It's caused by the impaction of these droplets, these supercooled droplets, being driven by the wind against the trees, and they impact on there to form what we call a Rime Ice deposit. Now during clear periods like this, just the mechanical action of the wind on the trees and the warming of, say, the tree trunks and the branches cause some of this deposit to break off. And you can see it here drifted in with some of the snow. So this is an important hydrological input as far as, along with the snow, as far as the snowpack at this elevation. This is just a close-up look of a couple inches of Rime deposit on an anemometer that built up over the course of an evening within one of these cap clouds, which were observed at the observatory. Following picture gives you a better idea of what's going on here. This is one of the instruments we use to measure wind speed and wind direction. So you can see something like 2 inches of rime deposit have built up on this instrument over the course of about 6 hours. Now the density of this rime ice and also its structural rigidity really depends upon a number of different factors. One is how fast the droplets impact. So it's important, which is obviously a function of the wind speed. Also, the density and mechanical strength depend on the droplet size and also on the temperature of the droplets when they impact. So we see rime, which can be rather dense like this, or more feathery and much less dense and having less structural integrity than this rime ice deposit. What you see here is built up on the propeller blades of this anemometer. And of course that makes measuring wind speed rather difficult. We have to bring these instruments into the observatory and knock the stuff off or knock it off outside in order to get a fairly reasonable estimate of the wind speed using an anemometer like this. Well, this property of the droplets, that is their fact that they're super cooled, allows us to sample the cloud water in these clouds. This is a collector that we designed and built for doing that. The distance from here to here is about 10 centimeters. And then on each arm of this collector there are 10 small ribbons which have about 1/2 millimeter cross section. This whole thing spins around when it's operating at about 25 revolutions per second. The ribbons are made very thin, so they have a very high collection efficiency for collecting cloud droplets, which have a size of about 10 microns in diameter. And you can see on the ribbons there, this is after the sampler has been running for about 15 minutes. You can see the white deposit, the rime that's built up on there. Now this is a picture of a cousin of the cap cloud. This is taken from Laramie looking towards the Snowy Range. This is a more extensive cloud system. It's deeper. It's also broader in horizontal extent, and we call these orographic cloud systems. The last few days have been some good examples of this. They also contain supercooled cloud droplets, but because the tops are much higher and therefore much colder, ice crystals can form and grow by vapor deposition from the supersaturated environment to form these pristine ice crystals that you commonly see if you spend any time out here in the Snowy Range in the wintertime. Those crystals then get to a size where they start to fall at appreciable speeds, and so they fall through the cloud of supercooled droplets, and they also then accrete rime, forming a rimed ice crystal, and then eventually will form what's called a grapple, which is just really a lump of supercooled cloud droplets which have been collided onto this piece of ice, which originally was just a crystalline, an ice crystal which originated from the top of the cloud. Now, of course, these grapple particles have a fairly high fall velocity, so these orographic cloud systems tend to be efficient precipitators. That is, much of the air that flows up and into the cloud and condenses is removed by this riming process on the ice crystals. Now, going up a scale further as far as precipitation systems, we can talk about more frontal type systems which produce heavy snowfall, say here in Laramie, and produce snowfall, say, over a very broad area, say part of the state of Wyoming or Colorado, that sort of thing. So there's this hierarchy of cloud sizes and the extent or area which they affect. Both the orographic clouds and the cap clouds are, by definition, confined to mountainous regions where the mountains lie perpendicular to the westerly wind, and therefore that's where the clouds form. Now, in summertime, things are different because clouds tend to be much more convective. This is a picture taken of Elk Mountain. You can See a little bit of the remaining snow in some of the gullies on the east side here. This cloud is impacting the top of the mountain, but it's not forming rime because the cloud is warmer than 0 degrees centigrade. Also, this whole convective cloud is very deep. It may extend upwards to 5 or 10 kilometers into the atmosphere. So, and of course, these summertime clouds also produce abundant amounts of precipitation, but it's very localized and also only lasts for maybe a minute, several tens of minutes, upwards to an hour. Now, we've studied the frequency of these summertime cloud immersion events because there's some interest by people in the biological community of trying to understand acid deposition in the form of cloud droplet impaction. So they're interested in the frequency of cloud immersion events during the growing season. So we've looked at this frequency and, say, compared it to the frequency of cap clouds. Well, cap clouds in the wintertime occur something like, on average, about 1 day in 3. These summertime cloud immersion events, which are associated with convective clouds, occur like 1 day out of every month. There's a frequency of about a factor of 10 less than the wintertime cap cloud events. As far as deposition goes, I've shown this picture here of the NADP site at West Glacier Lake. This is in the Snowy Range. This is a site operated by the Water Center. NADP stands for National Atmospheric Deposition Program. And they're, of course, interested in deposition in the form of acidity and the other chemical constituents associated with acidity, especially in high alpine areas, which are known to be much more sensitive to acid deposition, say, than lower areas where the soils tend to be thicker and the lakes have a much higher, or streams have a much higher acid neutralizing capacity. Now, I've used the wintertime data from this site, which is collected in these buckets once a week. So the wintertime snowfall composition data from the snow deposit, to compare it to the cloudwater composition observed at Elk Mountain. Now, I think this is a fair comparison. I know it's a fair comparison because we have some snow data from 1980 that compares rather well with the snow data from the West Glacier Lake site. And in the following slide, you can see this is the average ionic composition of cloudwater at Elk Mountain. Some 132 samples collected over the last 4 years. Winter season, 4 years between December and April. And the lower 2 rows of both cations and anions in snow are from the West Glacier Lake site. Now, the most striking thing about this is for all constituents, there's a much higher concentration in the cloudwater than in the snow. And the other thing that's interesting about this is that the base cations, that's the sum of twice times the molar concentration of calcium times twice times magnesium plus sodium plus potassium, is the dominant cationic constituent in the snow. But on the other hand, the cloudwater, both ammonium cation and hydrogen ion are the dominant cationic constituents in cloudwater. So the deposit produced by snow and the chemical deposition that results from that snow is different from the chemical deposition that results from impaction of supercooled cloud droplets on trees and other surface obstacles at sites like Elk Mountain. Now, the other interesting thing that you probably notice about this is that sulfate and nitrate are dominant anionic species in both snow and cloudwater. But in both cases, on average, there's an anion deficit. And we've looked into that in some detail, and I believe that part of that's due to the fact that in the spring, especially in the springtime, there's enough of this dust stirred up from the playa lakes and these alkaline deposits around Elk Mountain to produce actually a net alkalinity in some of the samples. And neither at our lab, much of the analysis is actually done at the observatory, or at the NADP lab do they analyze for bicarbonate anion. So that explains at least part of this anion deficit that you see here and over here. But it's still an issue which really needs to be looked into. We need to know where that material is coming from, and especially in the springtime samples. Now, the other constituent which the NADP lab does not analyze for is the acid anions, the organic acid anions. And we've looked a little bit at that. Now, on the far right, just to the right of chloride, you see formate anion. We've detected significant quantities of formate in wintertime cloud water at Elk Mountain. So that helps to explain the apparent anion deficit, but doesn't go all the way in doing that. It's also interesting to note that the few summertime cloud water samples that we've collected, this is using a different type of collector. It's not a rhyming type collector, but it's just a collector that impacts cloud droplets on a filament. It drips down into a container, and then we analyze the liquid. In those summertime samples, the organic acid anion concentrations of the organic acid anions was comparable to the sum of sulfate plus nitrate. So the organic acids are an important acid input in the summertime, and much more important apparently than they are in the wintertime. So as far as deposition goes, you've got deposition, which is commonly called wet deposition. That's the stuff collected by the NADP collection sites. There's some 7 of those sites in Wyoming. That can fall as rain in the summertime and could be graupel or snow, depending on how much rhyming occurred on the ice crystals in the wintertime. Now, there's also droplet impaction, because the cloud water carries, as it impacts and forms rime, it deposits that material on the trees, and then that material breaks off and adds to the snowpack. So we have droplet impaction as another mechanism of acid and chemical deposition as these other ionic constituents. Now, another mechanism of deposition is called dry deposition, where gases such as sulfur dioxide or the nitrogen oxides are diffused to the surface. They say stick on trees, and they stay there, and then might be washed off with rain, and then might be added to the soils with some subsequent precipitation event. Aerosols can do the same thing, particularly aerosols that just sediment, aerosols that have a large enough size so they have appreciable fall velocity. They can just fall to a surface and add to the net chemical deposit that accumulates on a surface. Dry deposition is a bit of a mystery. Droplet impaction maybe is something you are not as familiar with as well, and people tend to associate wet deposition with something we call acid rain, but the story obviously is a bit more complex than that, especially in these alpine areas where the wind speeds are high, cloud frequency is large, and also precipitation rates are large. So we have to look at all these processes if we want to analyze what, say, the impact might be as far as what the impact is of acidity, particularly in these sensitive alpine areas. Now, the gases, SO2 and the nitrogen oxides, of course, result from burning of fossil fuels. SO2 in particular comes from burning coal for power generation. Now, you hear a lot about the fact that in Wyoming we burn low sulfur coal, but Wyoming, the emissions of SO2 in Wyoming are larger than in Colorado by some 50%. I assume that in Colorado they probably burn a lot of petroleum, which has less sulfur for power generation. I know that's true in the Denver area. The nitrogen oxides, the sources of nitrogen oxides are much more diffuse. They tend to result from cars, people, any sort of combustion process, but the primary one being cars. So there are cars everywhere, but those sources of those materials, particularly nitrogen oxides, tend to be in cities and towns. Now, if you look at the amount of SO2 released in Wyoming, which, and if you would say deposited over the whole surface area of Wyoming, the deposition rate of sulfate for the whole state would be some 110 moles of sulfur per hectare per year, something like that. Now that's obviously less than the deposition you would expect for like a state like Ohio, where the emissions of SO2 are some 5 times greater than they are in Wyoming, or say in Arizona, where the emissions are some 7 times greater of SO2 than they are in Wyoming. Now these gases, SO2 and the nitrogen oxides, are either dry deposited directly to the surface, where they react chemically to form sulfate and nitrate, or a majority of them are converted by oxidation processes to sulfate and nitrate in the atmosphere. So just to show you where Elk Mountain is in relation to the sources, this is Laramie here. The Wyoming border sits down in this area down here. The Snowy Range is this high area above 9,000 feet here. Sheep Mountain, Elk Mountain, Rawlins, and then out here near Rock Springs, we have the Bridger power plant. And then in Kemmerer, there's a power plant. And in the whole Green River Basin area, there's a number of industrial plants called gas sweetening plants that release a lot of SO2 as well. So a large majority of the SO2 emissions in the state of Wyoming come from this area upwind of Elk Mountain. Now another source of sulfate, in addition to oxidation, say, of SO2 to sulfuric acid in the atmosphere, would be just sulfate, which is released as, say, dust aerosol from these arid playa lakes in the Red Desert area out in here. Now that sulfate tends to be neutralized. It tends to be something like sodium sulfate or calcium sulfate. It's not associated with hydrogen ion, but it's associated with a base cation. Well, looking at, now this is the cloud water data from Elk Mountain. And I just want to point out a couple of things about this. This is samples from the last 4 years, some 132 samples. The dotted line is the regression fit of the data, which in some cases is not very significant. But consider the correlation between nitrate and sulfate in the upper left-hand corner here. As you can see, the nitrate to sulfate ratio is less than one would expect based upon what we know about the emissions from Wyoming. In other words, sulfate is enhanced relative to the nitrate to sulfate ratio in the emissions. Now, part of the reason for that is probably just because there's sulfate in this aerosol generated from the Playa Lake, from these lakes that release dust into the atmosphere. Another reason might be the fact that SO2 is released into large stacks from these power plants, whereas the nitrogen oxides are released from automobiles and tends to be confined in cities and can be dry deposited rather efficiently in cities, whereas the SO2 tends to be transported long distances and transported very efficiently. So we see evidence for our industrial activity also in that same figure by comparing the nitrogen to sulfate ratio, nitrate to sulfate ratio, as observed in wintertime precipitation at the Alsea NADP site. Now this is a site in western Oregon, which is probably fairly representative of the clean conditions over the eastern Pacific Ocean. So as you can see, there's some enrichment of nitrate relative to sulfate. For example, as an air mass advex from the eastern Pacific region over the continent and to Wyoming. Now there's some evidence in the lower left-hand corner, for example, where I plotted chloride versus sodium for this marine source. You can see that some of the samples have a 1-to-1 chloride to sodium ratio, which is what one would expect from an aerosol generated in marine areas. However, most of the samples, and as indicated by the regression line, the base cation sodium here is enriched relative to chloride. So this enrichment of the base cation concentrations relative to the composition of seawater is indicative of precipitation and also cloud water collected in continental areas, and seems to suggest that this source of aeolian aerosols, that is soil dust, that sort of thing, is which contributes the base cation, is important in this area. Now this is a snow composition, and now, of course, the concentrations are much lower, but I'm just really interested in ratios of concentrations to look at possible sources. Again, in the upper left-hand corner, the snow, in most cases, the chloride to sodium ratio is less than one would expect based upon this composition of seawater. Most of the samples plot out in here, and that's consistent with what we've seen in the cloud water. Another interesting observation here is that calcium apparently is enriched relative to the calcium to magnesium ratio is larger in the snow than it is, say, in the cloud water. And this suggests some fractionation of calcium magnesium during the process of both cloud droplet formation and the subsequent transfer of droplets to snow via the riming process, to grapple via the riming process. Or it could suggest that the snow, as it falls, say as a pristine ice crystal, may collect aerosol that have a different a larger calcium to magnesium ratio than the droplets, cloud droplets, acquire due to any scavenging process that they undergo in cloud. Well, now comparing, this is sort of the upshot of the whole talk, comparing deposition of these 7 ionic constituents due to surface riming and deposition in moles per hectare for a seven-month period, November to May. That's the study time that I've been involved with at Elk Mountain Observatory. You can see, for example, deposition due to surface riming, about 50 moles per hectare, is comparable to the estimate of deposition due to chemical constituents that are transferred to the surface via precipitation. Now, basically, this is just simply is a reiteration of the fact that concentrations of all ionic constituents are higher in cloud water than they are in precipitation. The same is true for sulfate and nitrate. For example, calculated deposition of sulfate is 27 moles per hectare for that 7-month period, or on average anyway, as compared to 60 for deposition of sulfate via precipitation. Now this is a slide that I put up here just to remind myself. This is a picture taken looking up that Halleck Creek drainage, and what I want to say here is that it's really a very windy area at Elk Mountain. We've seen what the consequences of that is, that droplet impaction is an important mechanism of acid deposition to this ecosystem. But as atmospheric scientists, or as an atmospheric chemist, we really want to know or be able to have some predictive ability as far as saying what is the relationship between emissions of, say, a gas like sulfur dioxide and how it's deposited in these sensitive areas. Now, one way to tackle that would be that question would be to look at, say, trends in deposition data, say from the NADP sites, to look at how those, say, deposition of sulfate varies with changes in industrial activity. And people have done this kind of thing. They've looked for correlations between copper smelting, say in Arizona, and sulfate deposition in the Colorado and Wyoming Rockies. And there may or may not be a connection there, a significant correlation. Another way to approach that problem, to be able to say predictively and with some confidence what would be the effect of, say, reducing or increasing the emissions of sulfur dioxide would be to study atmospheric processes. Study how, for example, SO2 is converted to sulfuric acid in the atmosphere, and then study how that sulfuric acid is deposited to these sensitive areas. There's a connection between these two fields of study, and that connection would be to, say, study what the composition is of a whole drainage on a mass balance sort of sense. To say, look at what the composition is of the runoff in this small drainage that comes off the north face of Elk Mountain. So, with that, I want to just point out one example of an experiment that we've done to try to get some handle on how emission rates may affect deposition rates of one particular constituent, that's sulfate. Now again, I've just showed a picture of the cap cloud at Elk Mountain. We have this release site where we have released for very brief periods SO2 from right here. It diffuses up this drainage, is forced by the wind, it enters into cloud base, and then because of the high solubility of sulfur dioxide and also oxidants that oxidize sulfur dioxide, those materials diffuse into the droplets and therefore can undergo oxidation reduction reactions, actually into cloud droplets to form sulfuric acid. And we have a handle on knowing how long it takes this plume to transport from here to the summit, and knowing how high the cloud base is, we have a handle on how long the reaction time is. So we can essentially get a handle on or estimate reaction rates in cloud. Now this is just an example of the type of experiment that has been done. The top panel, well, the time over the top is 1.5 hours. Top panel shows gas phase concentrations of SO2 with a background here of about 0.4 of a part per billion by volume. Over this period, from here to here, we've released the sulfur dioxide from the Brush Creek site, and you can see the plume that results from it. So essentially what we're doing is, for a brief period, like 20 minutes, we're trying to simulate high sulfur dioxide concentrations that one doesn't normally see at a remote location like this. Well, that's fine and good, but the other thing we're seeing is we're monitoring the concentration of this material here, hydrogen peroxide, which was thought to be an oxidant for SO2, at least based upon laboratory experiments and some initial field experiments that were done by other investigators. And that it does appear to be the case. That is, we see a dip or a decrease in the hydrogen peroxide level, which is also consistent with the production of sulfate, which is shown down here during the presence of the plume at the observatory. So from this information, from the measurement of the depletion of hydrogen peroxide and also the enhancement of sulfate, can use that to try to figure out whether the kinetic data from laboratories in bulk systems applied to a cloud system are consistent with what we observe in the cloud. And that appears to be the case in this experiment here, and a number of other experiments. Now, in addition to doing experiments like that, we've been in a monitoring type mode where we've just looked at how much hydrogen peroxide there is in relation to how much sulfur dioxide. Now this is a time series that's very compressed. We're looking at, instead of an 1.5 hour interval, we're looking at like 3 days of monitoring. We're not intentionally trying to change the SO2 concentrations by releasing anything at all. But what we do see at the observatory, at this high alpine site, we do see these plumes which result from some source upwind, some power plant, some gas sweetening plant, maybe a refinery, for example, at Sinclair. We don't really know where the material comes from. The horizontal bars here indicate when there was cloud present at the observatory. So when we have cloud present, for example, in this interval here, when we have SO2, we see this depletion of hydrogen peroxide, which again is qualitatively consistent with what we know about the reaction between these two species in liquid systems. Now, this is data collected in January. I should point out that in general, at least, let's take, for example, here, between these two plume situations here, the concentrations of hydrogen peroxide are about 3/10 of a part per billion by volume, and SO2 is about 3/10 or 2/10 of a part per billion by volume. So the ratio, say, of SO2 to hydrogen peroxide is about 1. It's probably much larger here, but we really don't know what the SO2 concentration is because it's below the detection limit of our instrument, which is about 0.1 in these units. So except for these plume intervals, there is an abundance of oxidant relative to the amount of SO2 that's around to react with it. Now, it's even more evident in the summertime study that we did this January. So you can see here, again, this indicates the presence of cloud at the observatory, this horizontal line here. This is the SO2 measurement. We're at about 2 or 3/10 of a part per billion by volume. And the hydrogen peroxide levels are at 2. So we've got a hydrogen peroxide to SO2 ratio of about 10 or something like that. Now, hydrogen peroxide is produced photochemically, and those reactions are thought to be enhanced during the summertime when the sun shines for a longer duration, and also the zenith angle of the sun is greater at any given time during the day. So this is a significant result because it indicates if there were, say, for example, increases in sulfur dioxide emissions, which would produce increases in the ambient levels of sulfur dioxide, one would expect, because the amount of oxidant there is greater than the amount of sulfur dioxide, increases in the rate of oxidation of SO2 to sulfuric acid, and therefore presumably increases in the rate of deposition, rate of acid deposition. Now, it's been argued in the East Coast, especially in the wintertime, that this would not be the case, that if there were, say, decreases in SO2 emissions, that there would not be a corresponding one-to-one or linear decrease in acid deposition, because in the eastern United States there isn't that much oxidant around to convert SO2 to sulfuric acid. Or proportionately, there's not as much oxidant available for oxidation to sulfuric acid. Well, even in the extreme of winter, for example, that January case when we had a plume, I think one could argue that there might be a scenario something like this, where we have mountains capped by either orographic or cap clouds. This might be, say, the Sierra Madre Range in southeastern Wyoming, and this might be the Snowy Range, for example. And as this air parcel, say, transports from the pollution region around the Rock Springs area, carrying with it some SO2, which the concentration may be rather high because we're close to the source here. The air enters into a cloud, and we see a one-to-one or stoichiometric decrease in the amount of oxidant and in the amount of reductant. Now, in the clear air between the two mountain ranges, SO2 would either remain constant, there's really no reaction to consume it, or it may just be dispersed via atmospheric turbulence. So we expect this line either to remain constant if there's no sources, or to decline a bit due to just turbulent mixing. But at the same time, the oxidant can come up due to its production via photochemical reactions in the atmosphere. So even in even in wintertime, it would seem like the cloud regime is favorable for efficient conversion of SO2 to sulfuric acid. And in the summertime, we have so much oxidant around, there's really no problem in making that conversion. So in conclusion then, wintertime concentrations of ionic species in cloud water collected at Elk Mountain are 5 to 10 times larger than concentrations in wintertime precipitation collected both at Elk Mountain. That was the samples that I showed you in the regression fits of, say, nitrate versus sulfate in snow, and from the West Glacier Lake NADP site. Now, I just briefly alluded to the second point, and that is that organic acid anion concentrations in wintertime cloudwater samples are less than the strong acid anion concentrations. So it would appear that the acidity in the wintertime comes from sulfuric and nitric acid, not from the organic acids. However, there's evidence to suggest that the organic acid anions are dominant in summertime cloudwater samples. Now, this is just based upon one sample that we collected this July. But that enhancement of the organic acid anions is also consistent with what we know about the photochemistry in the atmosphere. And also the precursors for those acids tend to be emissions of, for example, isoprene from trees, which go up in the summertime when trees are, for example, deciduous trees are active. And 3, deposition of acidity and nutrients. Now, when I say nutrients, I think it's something like ammonium or nitrate, something that might be limiting in a biological sense, via riming on trees is comparable to the flux of ionic species in wintertime precipitation. Now, this is just a result of the fact that concentrations are higher in cloudwater than in snow. And finally, except in midwinter and during episodic pollution events, and we saw a few examples of those, gas phase concentrations of hydrogen peroxide exceed gas phase concentrations of sulfur dioxide at Elk Mountain Observatory. As a result, production of sulfuric acid does not appear to be oxidant limited either in the wintertime and especially not in the summer. So.
Okay, thank you very much, Jeff. So we have some time for questions.
Go ahead.
Yes, so you showed a figure of concentrations of SO2 downwind of power plants in Rock Springs and Sinclair refinery yet.
Yeah.
Around the Wheatland area, those concentrations were real low, and Cheyenne also. Either why that is?
Well, I don't have data for Wheatland. Are you saying you do, or?
No, I was looking at your figure, and their concentration in that area was shown as very low. I just wondered if...
Well, our measurements are all from the observatory. They're all taken from there. We don't have any measurements at any other sites. We do know where the sources are. And one very close source is this refinery at Sinclair. And I would imagine, just on what I know about the airflow, that air is flowing, westerly past Elk Mountain, and it's going down into the North Platte and Laramie drainages, and it ends up down in the Wheatland area. But during that transport, one would expect more dilution of the contaminant from those power plants. So it may be true that SO2 concentrations are lower at Wheatland due to the sources that are in the Rock Springs area. Now, I don't know what sources are there in Wheatland.
Well, the Wheatland power plant, I just wondered if you were showing that there was data over it.
No, I don't have it. You're right. Yeah, that was a time series. See, it wasn't concentration versus distance. It was just concentration versus time at Elk Mountain Observatory. Yeah.
You showed that, essentially the result is that the cloudwater concentrations of most of the solutes are much higher than in your standard precipitation like snow.
Right.
Presumably the existence of those solutes, at least in the atmosphere, must be fairly constant. What would be maybe I missed it, but what's the mechanism of essentially a partitioning?
Right.
Such that
Right.
solutes are much more, or at least the infinity for the solutes
Right.
in
Right.
cloud water is much greater than...
Yeah, no, maybe I went over that. I probably didn't even mention it. I meant to mention it. But when I had the slide up there where I showed the 3 boxes, we had the cloud water to the left, and the middle box where we had the gases SO2 and NOx, and then the aerosol. I didn't say this, but that aerosol that the cloud droplets form on tends to have a composition that looks like ammonium bisulfate. So you have sulfate, and then the corresponding cations are ammonium and hydrogen ion. So the cloud droplets that form do by diffusional growth as the air enters into the cloud, essentially forms on this aerosol and starts as a very concentrated solution of ammonium bisulfate, which then dilutes as the droplets grow via diffusion. Now for the snow, the story is a little bit different. The snow, if it's grapple, the composition can look a lot like the cloud water, because the grapple is just was cloud droplets that were just collected via the fact that the crystal fell through the cloud. But if the snow is those pristine snow crystals that you think about when you think about snow, those hexagonal kind of dendritic shapes, that snow, that water was transferred from the vapor phase to the crystalline phase via diffusion. And so and the original embryo, the nucleus for that crystal, at least there's really not much known about that, but that aerosol was probably sort of a mineral component that had maybe sulfate, but whereas the corresponding cation was something like sodium or magnesium or something like that. So that explains why the snow is more dilute, because the snow acquires water via this diffusional process. The grapple acquires water via this collisional process. And so that explains the difference between. Yeah. So there's a fractionation not only of the water substance, but there's a fractionation of the chemical constituents due to the different scavenging, as we call them, the scavenging processes in the cloud. Those are the kind of things that you'd really like to be able to understand. At least you'd have to understand really well if you're going to be able to say something about how deposition would change. You'd have to know something about the aerosols. You'd have to know something about these processes in cloud. And you'd have to know something also about these reactions that occur due to diffusion of gases to droplets and liquid phase reactions.
You mentioned that emissions were what you, or deposition is what you expected for the type of emissions that we already had. Did you take into account any interstate?
No. Well, I'm waving my hands at that point. When I say that so many thousands of tons of SO2 from Wyoming relate to 110 moles of sulfate per hectare per year, that's all I'm doing. I'm just saying what comes. Wyoming is a big producer of sulfur dioxide for this intermountain area. But if you compare Wyoming to a place like Arizona, then there's just no comparison. I mean, it's like a sevenfold difference.
Well, the reason I brought that question up was you mentioned that later in your talk about copper smelters in Arizona, and they have traced emissions from Arizona of the problem in Wind River Mountains.
I think there's only a causal or statistical connection. Nobody's ever flown a plane, as I followed parcels in a Lagrangian sense. It's a very complicated, the transport meteorologically is very complicated.
Well, the way I understood it is someone had tried to use a radioactive tracer and they had found evidence that I don't know how they did it.
I don't know. I'd like to see I'd like to hear about it. That sounds. I mean, that's one way to solve the problem, because the meteorology is so complex, and it tends to be so episodic because you've got storms. Presumably the deposition is really not much unless you get some sort of precipitation. So, you hear a lot about that. You hear a lot about the connection between deposition in Wyoming or in Colorado, and I've seen the papers, and emissions from the border between Arizona and Mexico. And those deposition rates of SO2 fluctuate depending on the price of copper. And presumably the deposition of sulfate fluctuates in phase with that. And some people claim that to be the case as far away as the wind rivers of Wyoming. But that's only, it doesn't mean there is a mechanistic or doesn't mean there's a process that connects the two. It could just be a statistical fluke. Not that I'm skeptical of the results. I just think that more work needs to be done to invest. Maybe that's the kind of experiment that needs to be done. To use a tracer that can be traced over 1,500 kilometers of distance. You know? Interesting thing about those papers is that there's also a connection between calcium and smelter emissions. But smelters don't release calcium. That is, the levels of calcium precipitation go down when SO2 emissions from smelters go down. So there's got to be something else going on there as well. There's got to be, I mean, there's obviously a lot of complicated chemistry and physics between what comes out of the stack at some smelter in Arizona and what gets to Wyoming.
Okay, if there are no further questions, thanks again, Jeff, for your talk.
Thank you very much.